So we are carrying on in the third lecture of this course on applied electromagnetics, and we have been talking about vector fundamentals. So we will carry on with that vector fundamentals. So here we will cover the things that we did not cover in the last class, and also hopefully you have seen the YouTube lectures which have been uploaded and got familiarized with these vectors, and you have been learning vectors since your high school little bit, but we will be applying the concepts of vectors very much in this course. Okay, so please pay attention. So this is my lecture 3. Of this course, and today we will be talking about triple products of vectors. The numbers multiplication is very simple, whereas vectors multiply in two fashions. One of them in scalar fashion, yielding a scalar value, which is a scalar number. Scalar is basically only magnitude. And vectors, when they multiply, that is in the dot fashion, when they multiply, they get the scalar value. But when they multiply in cross fashion, they yield a vector. So multiplication of vector is well defined in that sense. Okay, and they carry meaning. So today what we are going to talk about is not multiplication of two vectors, rather multiplication of three vectors, A cross B cross C, for example, or A dot B cross C. Okay, so that is the triple product, number one. Number two, what we are going to talk about is scalar and vector projection. Scalar and vector projection. We'll talk about. This is very essential concept in analyzing field concepts for this course on applied electromagnetics. That's the reason why we are learning this vectors in depth. When you come to, you will be dealing with a lot of physical quantities, especially it's all about field, magnetic and electric field. That's what is all about electromagnetics. The sum and substance is all field, and the field is actually specified by a vector quantity, cannot be specified by only by a scalar number, because it varies not only with magnitude but also at every point in space has a unique, the quantity has a unique direction associated with it. So therefore we have to define a vector field for the electric and magnetic fields. Now we will also deal with what is the significance of this triple product, scalar and vector projection. That is another concept. Then what we will be talking about is the concept of position vector, because whenever we talk about field quantity in applied electromagnetics, we will come across a term called the source that is the source for the field. So there must be a source for the field, and that must be located at some position at some point in space. And with respect to a origin or a reference point, we will have to define what is called the position vector. And then we want to find the field at another point in space due to the presence of the source. So that point is referred as the field point. So we have or the test point. So we have a source point, we have a field point. Okay, so we have to apply the concept of position vector over there, and also we should also be able to understand the concept of displacement vector. Let us say I move a charge from one point in space to another point, then I have to define by what is known as the displacement vector. Then also we need what is called separation vector, because why do I require separation vector? Because with respect to origin, I know what is the source point. With respect to origin, I know what is the test point. Now I want to find what is the separation between the source and the test point. Okay, then I need to define the separation vector. So we will learn this concept. All of these things you have learned in mathematics, but this is just talking about, and then we'll do a couple of problems. So let us begin with triple product. So given three vectors, A, B, C, A, B, C, given three vectors, and we want to define, we can define two types of triple product. One is the scalar triple product. And it is defined as A dot B cross C. A dot B cross C for this. And this is a dot operation. This is a cross operation. So because I had written the bracket, normally what you do is in mathematics, you first address the term within the bracket, and B cross C will yield a resultant vector. Say, let us say the resultant vector between B cross C is actually R. This is my resultant vector, which is actually B cross C. So once I know B cross C, I can actually do this. So this is my resultant vector. Once I know this value B cross C, then I can take A dot R, and this is a dot operation which will result in a scalar quantity. So scalar triple product, the name scalar comes from the fact that the dot operation leads a value, only a number. Okay, and a triple product, because we are dealing with three vectors, therefore it is triple product. So it is a combination of both dot and cross operation. Now one more, the more elegant way of doing this A cross B cross C is A dot B cross C, sorry, A dot B cross C. The more elegant way of doing this is by what is known as the determinant fashion. And let us say I define the components of A as AX, AY, AZ. Similarly, I define vector B, the components as Bx, By, Bz, and vector C as Cx, Cy, Cc, subscript. And then the determinant of this will give what is this value. So this is a single step solution. Instead of doing two operations where you first find the cross and then take the dot, you do this determinant evaluation, you will get this value. So this is the definition of the scalar triple product. Now you can easily do the determinant value. You will get a, so because this like a determinant and you get a single value for evaluating this. This like a box. It's a 3 cross 3 matrix determinant. You get a value 3 cross 3. So you will get a, what is called a value scalar quantity. What does this scalar quantity signify? We'll come to that. So this the other name for this, therefore, is what is known as box product. And so you will get essentially this quantity, scalar quantity you will get, and you will get a number. So this, the significance is it gives the volume of parallelepiped, volume of a parallelepiped, defined by the edges A, B, C. Volume of a parallelepiped. So that is about the scalar triple product. I'm sure that you have understood. Now, what is the vector triple product? Vector triple product is actually given three vectors. It will be all cross A cross B cross C. Okay. Before that, I need to tell you something. Because this is determinant, the property of the determinant says moment you interchange the rows one time, let us say I interchange the rows between A and B, then the value of that determinant will be minus of the first initial value. So whatever value. Now if I do two operations, I will get what is called the minus of minus, it will become plus. So I want you to understand this, that this A cross B, A dot B cross C is actually can be represented more elegantly. So let us, I will use this space for, okay, let me do one more thing. Not to confuse you, I can insert a slide over here and so scalar triple product A dot B cross C, something I needed to tell you just for the sake of completion. We can this is written A, B, C more elegantly equivalent to B, C, A equal to C, A, B. Okay, so what I have done is you can check this. For example, I want you can prove this very easily. Okay, you can interchange the rows, you will get this. So this is what is called that, the cyclic nature, and this is a box product. You will get a value. So however you operate, it won't be, the minus will be removed because you interchange twice. So you can prove that easily. So I want you to think about it. Vector triple product, what we do is we can actually first, you can simply take, so I need to define whether this is, if I put bracket here, it may not be the same as this. Okay, so you have to be very careful. Moment I have this A cross B cross C, the best way for this is what is called B A dot C minus, this is a rule. So you can prove this vector identity C A dot B. You can expand this and you can get this, you can prove this. So I leave it to you to prove this because I don't want to spend too much time on this. So we might invoke this rule as and when essential. This is what is known as back minus cab. So if you take a cab, a rental taxi, you normally sit in the back. So you put yourself up front. So it is called back minus cab. So this is something you can easily remember that way, right? So back minus cab rule. Now what is A dot C? You will get a scalar number and B is a vector. I multiply a scalar number with a vector, I will get a vector. And similarly, I will get a scalar here, A dot B. I multiply with vector C, I will get a vector. So two vectors I subtract, I will get the resultant quantity, a vector. So therefore, the resultant quantity being vector, so this is what is known as vector triple product. Okay, so it involves three vectors, so triple product. The resultant quantity is a vector, therefore the name vector triple product. That's about it. Okay, so this has no physical meaning as such, but it's a mathematical concept that we might invoke as and when necessary. So again, this rule, if you remember, you can actually invoke the rule and for any three vectors that we will deal with when we talk about electrostatics and magnetostatics, likewise in electromagnetics if necessary. Okay, so that is about that. Now, what is the next topic? The next topic I want to define what is the position, displacement, separation vector. Position, displacement, and separation vectors. So let us say this is my point O. Okay, this is my point O, which is my source. Okay, and this is, let us say I take a Cartesian coordinate system. And this is my x-axis. So x cross y gives the z. So you can see anti-clockwise of a right-handed screw. We lift the screw up. So x cross y is z. So that is how you can actually. So this is what is called the right-handed coordinate system, Cartesian rectangular coordinate system, right-handed coordinate system. Now let us specify a point which is in space. Let us say that point is P. And this is, I have a test charge Q, source charge, sorry. This is my source charge. Some charge is there in space. And at this point P, which is defined in space as the coordinates is defined as x1, y1, z1. Now this is my source point P. Now let us say I have a test point Q. And this is my test point. So we will encounter or the field point. So at the point Q, I want to know what is the field due to the presence of a charge at the source point P. Okay, so that is how you define the test point, and it is defined as x2, y2, z2. So with I know a reference point O, from this point what I do is I normally will use the symbol. So this is my the way I write the vector. You got to be careful here. So I will use this always. Okay. So this is my practice. So this one is actually R prime. So the prime coordinate is always, I refer to it as prime coordinate. I always refer to it as the source. Prime coordinates define source. This is the way I define. Okay, and the unprimed coordinate, which is the test. So the vector connecting from the origin to the point Q. This is my unprimed coordinate R. So this is my point Q, unprimed coordinate R. So I use unprimed coordinates. This I will be following throughout this course. So please remember this notation. So there is a prime here, there is no prime here. Now the position vector is actually for the source with respect to origin O is going to be OP vector, unprimed coordinates, which is nothing but R prime. Define test. Okay, so I want to find what is the field at the point Q due to the presence of a source charge at P. So I need to know what is the separation between the source and the test. Now I have to actually invoke the law of addition of vectors to define this. So based on that, let us say what I need to do is, it's always drawn like this. Think about this. So from source, I have to define this. So if I define like that, so it becomes actually r prime plus this equal to r. So this vector must be equivalent to r minus r prime. This is the addition. Okay, addition of vectors result in this. So look at the way I have drawn the resultant vector. The head points to the test point, and from the source point I am starting. What is the separation? The separation vector is the r vector minus r prime vector. Right. So this vector is actually, I use this symbol, the small r. So this is my separation vector. Now these are all fundamental definitions we will need to invoke. Now how do I define this position vector OP? OP is defined as, vector OP is defined as r prime, and it will be defined as x1 hat plus y1. So actually, because this is Cartesian coordinate system, I have to simply remove this subscript in the unit vector, because this is all Cartesian coordinate system. Cartesian coordinate system, the unit vectors, they have same direction. Okay, x hat along the x-axis, y hat along the y-axis, z hat along the z-axis. So I need not worry about that. So I need to delete that over here. And this is y1 y hat plus z1 z hat. Similarly, vector OQ is r, and that is x2 x hat plus y2 y hat plus z2 z hat. Okay, now you can see the addition tells me that vector OP plus PQ source to test equal to vector OQ. So this is my vector r prime plus vector r equal to vector r. So implies r equal to vector r minus vector r prime. Small. Okay, so this is my separation vector. So I have, so these are my position vectors. This concept is very, very essential when we estimate the field at any point due to a current carrying wire. If it is a current carrying wire, then we define at a test point what is the magnetic field. If it is a charge at rest in space, then we define at a test point what is the electrostatic field at a test point. So in which case we need to invoke this position vector concept. That is why upfront we are putting these concepts. So separation vector is this small r separation vector. Okay, so this is about this concept, and this you can easily see that vector r is nothing but x2 minus x1, x2 minus x1, x hat plus y2 minus y1 y hat plus z2 minus z1 z hat. So you can easily find what is the unit vector, the direction of this vector you can find by simply taking the mod of this vector. Okay, so this actually vector r by mod vector. Okay, let me rewrite it. The unit vector simply gives the direction with a magnitude of 1. So this definition is actually given by vector r by mod of this vector. Mod of this vector. Mod of this vector can be square of this term plus square of this term, square of this term. Take the square root of the entire term. So that will be square root of x2 minus x1 square plus y2 minus y1 square. So mod of that vector, if I have to write it for just to ensure that for the sake of completion, you will have x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 square. That's about it. Okay. Now, what about, so we have defined position vector. We have defined the separation vector. We have also defined one thing that we need to define is still displacement vector. So displacement, let us say, I have this rectangular coordinate system. Rectangular coordinate system, we always invoke. We will see the other coordinate system in the next class. Other orthogonal coordinate system. You see, this is called orthogonal coordinate system because the angle between x and y is 90 degree, y and z 90 degree, z and x 90 degree. And this is a cyclic coordinate system, right-handed system. Okay, so this is my x-axis, y-axis, z-axis. So if I were to interchange, I have to interchange keeping the cross product in mind so that I will know whether the way I have written this axis notations are same, right? So think along that direction. So what is this displacement vector? So this is my point P. Let us say I displace this charge by a small P, which is my displacement vector dl along this direction. So this is the source was at P at t equal to 0. Now, if I move the source charge to point P prime, then that is by a distance, that is by a distance dl. Okay, or more specifically displacement, because we are talking about vectors, we will rather use the vector notation, more specifically displacement, displace by dl. Then we define in rectangular coordinate system, we define the infinitesimal displacement vector. The infinitesimal, we say infinitesimal because it is very small distance, infinitesimal displacement vector. dl prime as dl. I'm sorry. Okay, you can, it depends. Okay, so because we are talking about source, so let us use the dl prime, no issues. So we use, because this is like x1 we define, and we can actually say what is called dx prime x hat plus dy prime y hat. The use of the prime coordinate is for the reserved for the source. Prime coordinate define the source plus dz z prime z hat. So this is the displacement which we have encountered, and this will come. We have to invoke this when we deal with what is called the vector calculus. So how do I differentiate and integrate quantities which involve vector concepts? That is something that we will be learning through this course. You must have learned these things. So there are special ways of doing this vector differentiation and integration. We will deal with that as and in the upcoming classes. So vector calculus, we will be invoking this. And then we will be using this concept when we estimate the field and so many other things that accompanies this course. Okay, so we will be dealing with such things. Now the remaining thing, there is a problem. Let us try to do the problem quickly. Oh, components. Let me finish the component. Maybe problems we can deal it in the next class quickly. 10 minutes problem. So these scalar and vector components. Or rather projection. So I have a same thing. I have, let us say I have a vector A. So there is a direction given by this head. This is my starting point. The magnitude is given by the length of this vector A. And let us say I have vector B, which is like this. Vector B, and the way and the angle between this vector A and B is theta AB, be the angle between vector A and vector B. Then what we do is we take this vector B. I want to know what is the projection of vector A on B. Aim to find the projection of vector. So what I do is I bring this vector over here and draw like this. So okay, so I need to draw the proper parallel to this vector A. So otherwise I will be making no sense out of it. So let me redraw that. So I will be, here it is like this. So I have to be careful. So let me try my best. So this is my vector A. So this is my vector A. I want to find onto B. So this is my angle theta AB. Then all I need to do is project this vector onto this. So this is my projection vector on B. So I call this as vector A on B. The subscript B tells me that, so this is a vector projection. Now the magnitude of that will be the scalar projection, which is, so this is a vector projection, this one. This is the mod of that vector that will give the scalar component, scalar projection. Okay, so that is the thing. And how do I do this? So to do this, what I do is there are two formulas which I will give you, which scalar projection is basically vector A. Scalar projection, if I want to find only the AB, then all I need to do is it is A cos of theta AB. So this is mod A. So I need to take the mod A of that vector and cosine of the angle you multiply, I will get the scalar projection. So this is my scalar projection. This formula is my scalar projection. And the vector projection is nothing but, so mod A cos of theta AB, and vector projection is nothing but actually very simple. All I need to do is I multiply this vector. So mod A, I want to find only vector. So how do I do that? So vector projection I need to do. So vector projection is given by simply because this is a vector projected onto this vector. So and that projected vector is along B. So the unit vector along B is AB hat. So all I need to do is whatever I get the scalar projection, I need to multiply that with this unit vector. So I will do that way. Cos of theta AB, and whatever number, this is a scalar projection. This quantity which within this bracket is my scalar projection. I need to associate a direction that will be along direction of the B vector. So that will be just multiply the unit vector. So that is my vector projection. Now the perpendicular component is actually, you can use the law of addition of vectors. So this is my vector A, and this is my projection of that vector B on B, on vector A on B, sorry, and the perpendicular vector will be like this, sorry. So my stuff is really pathetic here. We'll finish in a minute. So this is vector A, and the projection of this vector will be like this. So over here, moment I do this, this is my vector. So this vector A. So the perpendicular component, if I have to project of this vector, this is my vector. So this vector plus this vector will be this vector. So, but you can see that this is in this case, this is going to be smaller than this. So I rather have to put the arrow over here. That will make more sense. So you have to see very clearly how do I draw the projection vector. So I can't do this way. The arrow has to be upward. The reason is very simple. I want you to think through, not downward. Okay, so it is not downward, it is upward for this arrow. The reason is very simple. I want you to think why it is like that. Because the magnitude of vector A is greater than the projected vector of A on B. So therefore, this plus this must give the resultant of this. Basically, horizontal component plus vertical component should give the resultant vector. So this will be my vertical component AV will be equivalent to vector A minus vector this my horizontal. So I can easily find the vertical corresponding. Okay, so with that I complete today's lecture. We'll do a couple of problems in the next class before we jump on to the next topic. That will be the orthogonal coordinate system, other than what you know, which is the rectangular coordinate system, which you are familiar with XYZ, but we will be dealing with curved surfaces. Therefore, we will be introducing the concept of cylindrical coordinate system that will be my lecture 4 on the YouTube. You are welcome to go and have a feel for that lecture. Okay, so that's about it. Just a second.